Hi, in this video, I am going to talk about what is cross-validation and what are the types of cross-validations you can use while building machine learning models. So first I'll talk about what is cross-validation and then we'll go into the details of the types of cross-validations, and we'll discuss four types of cross-validations. So what is a cross-validation? If you are familiar with building statistical model or machine learning model, you must already be knowing what cross-validation is. Just to do a recap or just to give you a brief introduction of about what cross-validation is just that you want to validate your model that it's going to work perfectly in future or not. Okay, so when you build model in historical data, so you build model in historical data, right? So the data that we have already seen, but the model is going to be used in future data. So the data that we haven't seen yet, okay, it's not seen yet, whereas this is already seen or this is already realized, right? So it's important to know if the model is going to do well in the not seen data or data that is going to come in future. So in order to ensure that it works there, we need to hypothetically create let's say a historical data, a future data out of the historical data. So we need to hypothetically create future data from the historical data. So if you have historical data, so we just divide and we build model assuming this is only the historical data, and we do not show the model or we do not use the second portion of the data, this portion of the data, to the model or to the algorithm, and we consider or we at least assume that this data, the second portion of the data which is not being used in model building, is going to be very similar to the future data, and if the model works good there, then the model is expected to do well in future as well. So that's the idea. I mean, the idea is just to ensure that the model works well in a new data set, completely new data set, right? It need not be the same data set, it could be a data from different time period also, that could also be the case, but it's just that it has to be an out of sample or out time that means different time or different sample. Okay, so it helps selecting the best fit model. The best model that we choose has to be well validated. It also helps ensuring that the model is not overfit. That means the model is working very fine with the historical data or the training data in technical sense when we call it as training data, whereas it doesn't perform well in the data on which we validate it, right? If that is the case, then this is a typical case of overfitting. So to avoid all these things, we need to do the cross validation, and there are many ways of doing cross validation. Four most important ways are the following, and I'm going to discuss these four ways. One way is the holdout method. The second one is the k-fold cross validation. The third one is the leave one out cross validation, and the fourth one is the bootstrap method. Okay, I'll go one by one. The first one is very popular, and I'm sure if you have ever built a model, you must already be knowing this one, just that you may not be knowing the name of it, but it's probably the trivial one. What do? You divide your sample into two different samples. One is training sample and the second one is test sample or holdout sample. Okay, you build a model in the training sample. So the training sample could possibly have 50 to 60 or 70% of the data, and your holdout sample could be having 30 to, let's say, 50% of the data. Okay, and there is no overlap. That means an observation that is part of the training sample is not part of your holdout sample, right? So the observations are mutually exclusive. That means there is no common observations between these two samples. Okay, so you build a model in training sample, and you see how it performs in the holdout sample. Okay, so if it performs well and it's consistent, the performance is consistent across training and holdout sample, we say that the model is good and it's well validated. It's a good model for future. So that's holdout method, but it has some issues. The issue is with this sort of validation technique is that Well, it all depends on how we choose the training sample. Well, we have just taken the left hand portion of the data, a training sample. Okay, so if we just for imagine we take this portion as the training sample, whereas this one would be our holdout sample. In that case, the model might perform, or model might behave differently. So the one thing that's lacking here is that it all depends how you choose your training and holdout sample. So it might be the case that the for a given for a given model, if you keep on changing the training and holdout sample from the same main sample, the performance could vary, and that's an issue, right? So that issue can be eradicated by using what is known as k-fold cross validation. So the main issue that we faced in the previous one is that we just have one training and one holdout sample, right? One training and one holdout sample. So depending on how you choose the training and holdout, you get the performance, and that could vary if you keep on changing the training sample and the holdout sample. Now in k-fold, we divide the entire sample into k different subsamples, and k could be 5 to 10. So there could be 5 samples or 10 samples. Now what we will do is that we'll have several training data sets. Okay, so we have just divided the sample into 5 subsamples. So we have 1, 2, 3, 4 and 5. Okay, now we have used the fourth subsample as the validation or holdout sample, and the other four samples as the training sample. So we will build model using the 4 subsample, the first, second, third and fifth, and test the model on the 4th subsample. So that's the validation one. Now we keep changing the post. Okay, so now we'll make this one as validation or holdout sample rather. Okay, but this one will make it as training. So now we'll build the model on first, second, third and fourth model, and we will use 5th subsample as holdout sample and test our model, and we keep on doing that, right? Now the good thing with such cross validation is that each portion of the sample is now part of training data as well as holdout data. So all the subsamples will be training as well as validation, right? We'll keep on changing, but there will be 5 iterations. However, each data point will be part of both training and holdout. So there is less likely to be selection bias, right? How we select our training and test sample, like the previous one, where our selection of training and holdout sample used to bring this issue of performance issue because of changes in the selection. But here that problem won't be there. Now, so the advantage is that it matters less how the data gets divided. Okay, it doesn't matter how you divide data. So if I have a sample, you're not sure whether this much you will take training and the rest you will take holdout. So how can you decide this much is just training? So that selection bias or the decision about how to take training is now immaterial. It doesn't matter in a k-fold selection. So selection bias is the main advantage, just to remember. So leave one out, cross validation, the third type of cross validation. Now this is more of a a generalized case of a k-fold cross validation. Instead of just taking k equal to 5 to 10, okay, these are small numbers, right? In a sample of million observations, if you just have 5 to 10 such samples, subsamples, then it can well be scaled up to more number of subsamples, right? And the most general case is that we'll take each observation to be a small subsample. Okay, so if I have, let's say, 100 observation in your main sample, then we'll divide the data into 100 different parts. Okay, and then the rest of the observations, okay, will build model on rest of the observations except only the last observation. Okay, and that observation will consider as validation sample, and then we will calculate error. This will be error 1. Okay, now we'll change the post, we'll make it training, and we'll make this one validation or holdout. Okay, and then we will again calculate error 2, and we'll keep on doing that. Okay, so you'll have error 1, error 2, error 3, and so on. So the average error will be simply the summation of error. You can actually square it just to get a mean square error. So the average error is going to tell us what is the accuracy rate and what is the expected error rate for the future. Okay, and one thing you might be wondering, that isn't it very difficult to do? Imagine you have million observations, or you have maybe even 100,000 observations. So you will have to do the 100,000 times iteration. You have to build 100,000 models and do validation for 100,000 times. It's very difficult, right? So it's very computationally intensive. So high computation time is there. But it's one of the best way to validate, because each observation is now part of training and test data. Second important thing is that now you have more data for training, right? When you divide just by 5 to 10 times, so you have less data for training your model, right? Whereas here you have more data because you just have one observation to hold out, right? Rest all observations is part of training, right? So it combines the best thing about your previous cross validations, right? You get the best of both worlds. But the problem is computation time. But now we have massive parallel computing. Many cloud providers are now providing us computing power at a very cheap rate, right? Whether it's Amazon, whether it's Google, whether it's Microsoft, whether it's Apple, right? You can just train your model with their CPU and GPUs, and they have huge with a very low cost. But on your computer, that's going to take for hours, maybe days or months. Last one I'm going to discuss is the Bootstrap method. Now this is slightly different from the other ones. Okay, so there are few steps involved here. Given that it's slightly different from the other ones, I'll try to explain what the steps are. Okay, so you randomly draw data sets from a training sample, and each sample has same size as the training sample, and then you refit the model, and then you examine the model. 4 different steps. You randomly draw samples, make sure that the sample size is exactly same as the main sample. Now that's a tricky point. You might be wondering, why do we have to get the same size sample, and how is that possible? If that's possible, then why are we doing it at the first place? Well, I'll explain. Then we refit the model, and then we examine the model by taking the error rate. Okay, let me explain you by taking an example. So we have this sample S which has got n observations. Now we take subsamples, okay, from it with exactly n number of observations, and ensure and take as many as you possible. Okay, let's say we took 100 such samples. Now we have n observations. Now when we have n observations in the subsamples, we need not have all the observations present in the main sample be in our subsamples, because we are taking observation with replacement. That means if a data point 1, let's say data point 1, data point 2, we have such data point, right? N data points. So if data point 1 has been selected once, it can well be selected twice, okay, because it's with replacement. Okay, so there will be many duplicate data points in a sample. Okay, so even though we have n observations in our subsample, it is not exactly the same as the main sample. Okay, similarly in the second sample you will get data points. With replacement, that means every time you selected a point, there is equal probability of each data point being selected, right? Now that said, the subsamples will be completely different most of the times than the main sample, and then you build your model in each of these subsamples. If you have 100, you have selected 100 subsamples from the main sample by selecting random observations with replacement, then you will have 100 different models, right? 100 different models. Now one thing to remember is that we have not divided the sample into training and test as such, the way we used to do in the last three types. And that's the main difference between Bootstrap method from what we have learned in the other three. Okay. So what we do essentially here is that instead of having separate holdout sample, we just consider that the random selection of observation in each subsample make it very unique. So every subsample is unique in its own way, and when you take the average of your with your error, then that will be very close to what it otherwise could have when you would have taken the holdout sample. So that error will be taken as the prediction error, or that error will be considered as the expected prediction error. So you don't have to use validator model separately. That itself is considered as validation, right? Okay, graphically we'll try to understand. Okay, so so we have the main training sample. Let's say we have 5 subsamples, no, n number of subsamples, and then we have, let's say, b1 subsample having n observations. The initial main sample has gotten n observations, so each subsample has got n observations. Okay, now when you build model in each one of the subsample b1, b2, b3 to bn, you will get error like e1, e2, e3 and en. When you average the error, that is the test error or holdout sample error, or rather we call it as expected prediction error, right? And you might wonder, we don't get such expected prediction error from training sample, right? We do get that from holdout sample. But in this case, given the randomness, or given the fact that we have taken unique samples by choosing data points randomly, you don't have to separately validate it. The error rate from these training samples, the n number of training sample, will itself be counted as the expected prediction error. So these are the most important cross validation techniques that's used in the industry and in academics. There are also obviously many other ways in which validations can be done. So if you haven't subscribed to our channel, please do subscribe, and we are going to upload many more videos on machine learning, data science, analytics, statistics and mathematics. Thank you so much.